computer. All right, hello everybody at home. Hello everybody here. I was watching the COVID rates very carefully. Yesterday it was at 4.97, no, 4.75% positivity rate, and it's coming down. So it looks like we've gotten over the spring break hump. So maybe, just maybe, this number will get really low, like 1%. But anyway, it's improving, and so I will be lecturing without a mask on here. So that being said, let's go on to our next chapter. So at the end of the last chapter, there was a slide on retrosynthesis. Okay, retrosynthesis is a technique you'll need for the rest of organic chemistry. So I'm introducing it here because this is where I'm also going to introduce reaction tables, which you're going to need for the rest of organic chemistry. It helps keep reactions in mind. It helps to remind you what can do what the reagents are, what the starting materials would be, and what the products are going to be. So that's where we're going to look at right now. Okay, so the thing I skipped was this retrosynthetic step. And so when we do retrosynthetic steps, and I'm going to do it more at the end of this lecture here, is we look for places that we know we can do a reaction. So for example, on this one right here, we have, we know a reaction where we can use an alkyne as a nucleophile. And it says we can make this from any alkyne and any alkyl halide. So if we were to cut this here, what would the two reagents be? Okay, that's what we're trying to think of here. So we can do an alkyl halide, which would give us, let's do that one, and that would give us this other compound here. H5. So that's just the thing with a hydrogen there. So what reaction would we actually do on this? We would take our sodium amide, pull our proton off, turning this into our nucleophile, and then we do an SN2 reaction to get to that product here. But what if we wanted to start with just acetylene? Okay, that's just the 2-carbon one. Well, we could break this bond here, and that would break us down to acetylene plus an alkyl halide, bromide. So now we've actually gotten all the way back down to just acetylene and just the alkyl halide. So the forward synthesis would look something like this. H, sodium amide, and 2, and then 1, followed by our alkyl halide, which would give us this and that. And then our next step would be 1 sodium amide again to make a nice nucleophile on this side. And then our alkyl halide here, our cyclohexyl bromine, and that would give us our final product here. So when we're going forward, as we're going forward, we want to look at our reactions in 3 ways. Okay, we want to look at our reactions as what do I need? What's the actual reaction going to happen? So what's my substrate and what's my reagent? That's the forward way. Okay, and then we need to look at it, well, okay, what I want to have it so that I have this is my substrate and this is my product. And then I need to remember what the reagent was. So that's in the middle. And then you also want to remember saying, I have a reagent and a product. What was the starting material? Okay, so when we look at our reaction tables, you actually want to look at it in 3 ways. So when you go to Canvas and download this reaction table, you should do all the reactions from last chapter and reactions from this chapter, okay, because it'll really, really help. I love reaction tables because it gives you a bunch of information. So on this one right here, a reaction type is addition. Remember, we have 4 reaction types. Addition, substitution, elimination, and rearrangement. So we have 4 reaction types that we can put in this front bar here. And then what we started with, and in this case, we're starting with an alkene, and our general product is an alcohol. Okay, so what do we need to do that? We needed water and acid. And then does it have stereochemistry or regiochemistry? Does it do syn addition or anti-addition? Will it make the cis product or will it make the trans product? Will it make a racemic mixture? Will it make a one enantiomer? is their inversion of the stereocycle. That would be here. Basic mechanism, does it go by a carbocation? And then this is other, or what I like to call complications. Like this reaction cannot be run with these reagents. There's no polar protic solvents, it goes by a carbocation, something like that. In this case, other is the carbocation can rearrange, and then you put what chapter it's in. This is actually in chapter 8. So if you go through that, you'll be able to see that. In addition to that, okay, done. You will see that in the back of the book, there are 2 summary pages. This summary page is the one for alkynes that we're going to learn about, that we learned a lot about in these 2 chapters, right? So over here, we actually have the elimination reaction that would create an alkene. And then we're going to learn this reaction that would create a dihalide that then you can use to make our acetylene. And so by looking at the reagents and going from products to reactants, that from reactants to products and from starting materials to products, you'll be able to build your table. In fact, the one for all the alkene reactions also has the intermediate. I like having the intermediate under the other chapter, the other section, because then if I know the intermediate, I'll know that, oh, it has to go anti-addition or syn addition. Okay, so and so there'll be a lot of, and then in the back of in the end of the chapter, there's also these kind of summary slides here. Make sure you put everything that's in those summary slides on your reaction table, except for the carbenes, which we're not going to do. But anyway, questions on the reaction table. Okay, because I'm going to get all the way through chapter 8 today. And then on Monday, we're going to do some problems related to that. So having your reaction table already done and already looked at is going to help you with the problems we're going to be doing. Then we're going to start chapter 9 and we'll have a quiz next Wednesday. So, all right. So let's take roll. Here. Chat's open. Okay. Seat number. I'm still okay. All right. So now this whole chapter is about addition reactions. We learned how to use elimination reactions to make alkenes. Okay. And so we want to look at these addition reactions. And so in this case, we're taking that pi bond that we just made in the last chapter, and we're adding stuff across it. Okay, so one of the things that's going to show up on the first one carbon, and one of them is going to show up on the other carbon. Okay, so we're going to break this pi bond and make 2 sigma bonds. Okay, so in this of the 5 reaction mechanisms we have: add a proton, take a proton away, react with nucleophile with electrophile, rearrangement, and nobody. Well, the last one's the hard one. Break a bond to form a stable ion or molecule. Okay, so those are the 5. And so in this one, we're actually going to do the nucleophile with electrophile. Okay, so it turns out the pi bond is the nucleophile. It has the electrons. Okay, so we're going to be looking for things that have the, looking for electrophiles for it to react. So things with partially positive charges or positive charges. Okay, so our alkene is our nucleophile and they react with electrophiles. Okay, simple alkenes don't react with nucleophiles and bases that are themselves electron rich. Okay, so without a catalyst or something like that. And I'll show you what that means on the next slide. All right, so there's 2 ways we can add across our double bond. Remember, our double bond is above and below the sigma bond in between the 2 atoms, right? And so what we can do is we can add both things to the same side and give you syn addition where they're both on the same side, or we can add one to the top and then one to the bottom. Okay, how do you tell those apart? They have different mechanisms. That's how you're going to tell them apart. Certain mechanisms are going to have an intermediate that says I have to add them both on the same side or I have to add them on opposite sides. Okay, so I'm going to stress that intermediate that you have, or that transition state that allows you to go to that. Oh, and I'll be making a bonus video that is all the mechanisms for chapter 8 as a separate thing by itself. Okay, so in the case of arsine and anti-addition, it turns out that is going to affect the stereochemistry of our final products too. So that selectivity is going to be important. Okay, so these are all the reactions we're going to learn in this chapter, okay, today. So we have a nice simple ones like just adding across a double bond. Right here, we're going to add acid across a double bond. We took acid away to make the alkene. We're going to add acid back to make it back into the alkyl halide. We can add water across a double bond. Remember, the last reaction in the last chapter was dehydration of alcohols to make alkenes. We can also go the opposite direction. We can make a vicinal dihalide. Remember, vicinal dihalide are on adjacent carbons and geminal dihalides are on the same carbon. We're going to show you how to do a reaction where you have a halogen first and then some other nucleophile. A lot of the times it's water, and we call it the Halohydrin reaction, but it could be anything where we form that. Then we have this borane and an oxidation reaction. It's going to give us a specific type of alcohol, okay? So we have one type of alcohol here. This next reaction, the oxymercurization, demercurization, is going to give us a different mechanism than the other two. So we actually have 3 different mechanisms for making alcohols out of alkenes. Then we also have making diols and making these cis diols. We can do that 2 ways, actually. We've already learned catalytic hydrogenation in the last chapter. And then we can also do one thing where we actually cleave the double bond. And we cleave that double bond with a couple different reagents, but this is one of them. Okay, so I'm going to go through each one of these independently so we can see how they work and what our products are. So in the hydrohalogenation, it basically is a nucleophile reacting with an electrophile. Okay, so our double bond is the nucleophile. It's the nucleophile. It has the electrons it wants to make a bond. Okay, why is it attacking the hydrogen on that first and not the bromine on hydrogen bromide? Well, it turns out that this is a polar bond because hydrogen is not as electrophilic as bromine. And so we have a partially positive side over here, partially negative side over here. So what's going to happen is that is now our electrophile. So our electrons are going to reach out, start grabbing that hydrogen. When it does that, it breaks the bond with that. And what happens to the other carbon though? We generate a carbocation. Okay, so we have that orbital is empty. It took the electron away from it and made that sigma bond. And now we have our bromide ion. And now our bromide ion is now the nucleophile and our positive carbon is the electrophile. So the next step of the reaction is a fast reaction between the bromine and the carbocation forming the new sigma bond. Okay, so basically what we're doing here is we're doing 2 nucleophile reacts with an electrophile. But we can also look at it as a Lewis base reacting with a Lewis acid. The alkene is the Lewis base because of that lone pair because of that alkene willing to swing out and make a new sigma bond. Okay, and then on the second half, the bromine is the nucleophile that has the electrons that wants to reach out and make the new sigma bond. Okay, so it is just 2 different acid-base reactions going for Lewis acid-base reactions. In one case, the HBr is the Lewis acid, and in the other case, the carbon is the Lewis acid. So we just have to remember that we're switching our system as we go. Questions on that? Okay, now because we form a carbocation, we'll have an intermediate, which is our carbocation. And so our energy diagram has 2 humps on it. The first transition state is we're breaking the pi bond right here. We're making this bond right here, and we're breaking that bond right there. Okay, so the electrons from the alkene are reaching out and grabbing that hydrogen, and that breaks the bond between the hydrogen and the bromine. And when it does that, it generates this high energy carbocation right here. And then it has a much lower activation energy to react with products and go down here. Notice that most of these reactions are going to be exothermic because a pi bond is not as stable as two sigma bonds. So by going from a pi bond to two sigma bonds, we have an exothermic reaction. Okay. And then so questions about that transition state or mechanism. Now, because we form a carbocation, we actually have to figure out where or what regioselective reaction we have here. In the case of adding an acid to an alkene, we have a rule called Markovnikovs Rule. In Markovnikovs Rule, it's going to tell you that they're going to add the hydrogen to the carbon with the most hydrogens. You're going to add the hydrogen to the carbon with the most hydrogens. Okay, why? The reason is we're forming a carbocation. Okay, so we want to form the carbocation on the more substituted carbon. If we do it on the more substituted carbon, that gives us a secondary or a tertiary carbocation. If you did it the opposite way, you'd have a primary carbocation. So you can't do that. So you always add the hydrogen to the side with the most hydrogen, and that puts the halogen on the more substituted side, right here, the more substituted side. So in the Texas euphemism of them has gets works there as well. But I like to say on the side with the most hydrogens wants to go, be with his buddies. Okay. Now, the whole thing comes down to carbocation stability. Okay. So if we were to take our HBr and react it on this side right here, oops, sorry. Let's react it on this side right here, put the hydrogen here first. What we'd end up with is a primary carbocation. Okay. So that activation energy is actually much, much higher to get to and creates a much less stable intermediate. Okay. So what's going to happen is if you have enough heat in there, it might do a little bit of adding, but what's going to happen is this is a lower activation energy. So let's look at that side right here. Let's have it attack over here now, have the hydrogen go there. That gives us a secondary carbocation with a lower activation energy and a more stable intermediate. So because it has a lower activation energy, it's a much faster reaction than the reaction to form the primary carbocation. Okay. And because it's a faster reaction and our intermediate's more stable, we actually can end up getting to our final product. So it's all about carbocation stability. But what's the problem with carbocations? If they can rearrange, they will. Okay. So let's talk about the stereochemistry of this. Now, like when we did reactions before, when we did that SN1 reaction, we formed a carbocation and we said that we had stereochemistry was going to be racemized. We're going to have an equal portion of the R and the S because you could attack the carbocation from the top or you can attack it from the bottom, right? So because you can attack on both sides, in this case, we formed a carbocation. So it's going to do the exact same thing. It's going to be regioselective in that your halogen is going to be on the more substituted carbon, but it could attack at the top or the bottom, giving you a racemic mixture, 50-50 R, 50-50 S. Okay. And so anytime we form a carbocation, we're always going to get that for stereochemistry. So the regioselectivity is where the hydrogen goes and the chlorine goes. The stereoselectivity here is racemic. Questions on that? Okay, so now let's go to the next thing we have, which is hydration. So in hydrohalogenation, we added the hydrogen first, and then we added we formed that carbocation, and then we added the things. Turns out we're going to do a very similar process here, but instead we're going to use the polar bond between the hydrogen and the oxygen. The hydrogen is partially positive, so it is looking for electrons, And so our alkene is the source of those electrons. And in this case here, we're going to use acid as a catalyst, and we're going to end up with an alcohol in the end. This also follows Markovnikovs rule. The hydrogen is going to add to the more stable the carbon with the more hydrogens on it, and the carbocation is going to form on the more stable or the more substituted carbon. Okay, so it goes by a similar mechanism. So in the case of this, we're using water as a very weak nucleophile, but we're using acid to help promote the reaction. Now, another weak nucleophile is an alcohol. If we protonate an alcohol, turning it into a better reagent for this reaction, and I'll show you why on the next slide, we can actually make ethers instead. And the ether is going to be on the more substituted carbon because it follows the same mechanism. Okay, so let's look at the mechanism in detail. So in this case here, it is an acid catalyzed reaction, okay, which means you need a water and a drop of acid literally is enough to do this reaction, okay? So what we'll have is we'll have an alkene here. Okay. We have our alkene here, and we have our electrons from our double bond are going to reach out and grab the proton on a hydronium ion. Why the hydronium ion? It has a positive charge. It's the most positively charged thing in the solution. Therefore, it's the thing that's going to react with it first. Okay. So when it reacts with it first, it's going to generate our hydrogen is going to go to the more substituted side and generate our carbocation. Okay. So now we have a carbocation. And when we looked at those E1 and SN1 reactions, we said water was a poor nucleophile, but if it sits around long enough, it'll react. Well, here we're going to have the lone pair of the oxygen here form a sigma bond with that carbocation. So this is our electrophile now, and this is our nucleophile to give us this oxonium cation. So this is just a protonated alcohol. Okay. So if we have that protonated alcohol, what's going to happen is that water that we generated up here can act as a base and remove that proton, regenerating hydronium ion and giving us our neutral alcohol. Notice that this can then be used up here. If we did this in the absence of water, the alcohol takes the place of water. If we did it with an alcohol instead, that would take place of the water in all these steps, and you generate an ether. Questions on that? So because we have a carbocation, what do we have? We have a mixture of syn and anti addition. Okay, because wherever we added the hydrogen, we're going to have that carbocation next to it. So we have syn and anti addition mixture, 50-50. Now that's true for the hydrohalogenation reactions with acid as well. Okay, questions on that? Okay, so this is our first way to do an alcohol. So this is our first type of hydration, which is why it's up here. Hydration version number 1 is acid catalyzed hydration. The second one we're going to do is we're going to call oxymercurization demercurization. Okay, so what happens in oxymercurization demercurization is the mercury here is going to add across the double bond with this oxygen, and they are going to, and it has to be in the presence of water, it's going to add across the oxygen, leaving our mercury attached here and our OH attached here, Hg. Okay, so we do not form a carbocation. We do not form a carbocation. Okay, because we don't form a carbocation, there is no rearrangement. Okay, notice that the alcohol is on the more substituted carbon. The mercury acts as a hydrogen and goes with the carbon with the more hydrogens on it, and the OH goes on the more substituted carbon. That means we can get secondary alcohols when, if we formed a carbocation, it could arrange to a tertiary alcohol. Whoa. Sorry, thought I did that already. Okay, so you get a mixture of syn and anti right there. You don't need any acid. It's very good yields. The only problem is that mercury is toxic. Okay, and if you did the same thing with an alcohol instead of water, you'd make an ether as well. The big thing about this, it's different from the acid catalyzed one, is the acid catalyzed can rearrange, can form the more stable carbocation. This one can't rearrange. It's going to go just where your alkene was. So you're very selective about where it is. So this is a regioselective reaction without rearrangement. Okay. The type of hydration 3 is what we call hydroboronation oxidation. And so what we're going to do is we're going to add borane across the double bond selectively, and then we're going to oxidize the boron off to give us our final product. Okay. So in this case here, we're going to use a variety of reagents like borane, which is BH3, diborane, D2H6, and occasionally you'll see 9-BBN in the homework. It's this compound here. It only has one proton to transfer, so you can be very selective about doing only one equivalent. Okay. So in this case here, what we're going to do is we're going to take the hydrogen is going to add to here, and the boron is going to add to the side with the more hydrogens. So that's boron. And so it's going to have its groups on here like 2 other hydrogens here. So if we think about it, the boron wants to add to the outer carbon because of the steric bulk. It has these 2 hydrogens that are going to butt up against these groups here. So it's going to put them over with the hydrogens. So the boron always goes on the least substituted carbon, and that puts the hydrogen at the more substituted carbon. So that makes it anti-Markovnikov. It's backwards. Okay, and now when we oxidize it off with peroxide and a base, we get the alcohol on the least substituted carbon. That's completely different than the other 2 reactions, right? The other 2 reactions. So that gives us selectivity. Now, as we go forward here, and this is something why I like the reaction table and why you should build it, is that reactions are starting to get more selective. We want to use different reagents to get different final products. Okay, so let me demonstrate that. Okay, in the case of this, if we have our reagent here, we're going to give it on a secondary or tertiary alcohol. Okay, if it can't form another, if it can't rearrange to form a tertiary carbocation, it's going to stay as a secondary carbocation. Okay, the oxymercurization, demercurization, because the mercury was here, the OH is going to go on that carbon and that carbon only, no rearrangement. So you can get secondary or tertiary with this one as well, depending on your substrate. But with the hydroboronation, the boron's going to go here, and that's what's going to be oxidized off, so the OH stands on the outer one, the primary alcohol. It's the only way to make a primary alcohol we have from an alkene. So that's kind of cool. We now have selectivity. So how can we use that? Well, let's look at this substrate here. You can make primary, secondary, or tertiary alcohols if you use the correct reagent. Okay, let's think about this. Why is this creating a tertiary alcohol? Well, the first thing that happens is it forms a carbocation here, and we added a hydrogen here. Okay, we have a hydrogen here, so we're going to do a 1,2 methyl shift to give us our carbocation here, and our hydrogen is going to go over here now, giving us a tertiary carbocation. Now it's going to wait around to react with water and give us our OH group. So we get a tertiary carbon from this substrate. We get a tertiary alcohol from this substrate. What if we didn't want the tertiary? What if we wanted the secondary? Well, now we have to use the one that's regioselective with the mercurization, demercurization. We're going to put the mercury on here, Hg, have our OH here, and then we're going to reduce off our mercury, keeping it on that secondary site. No carbocation, no rearrangement. And then for this one here, we're going to add across where the hydrogen is going to go on this side and the boron is going to go on this side. And then, of course, we get to oxidize this off and give us our alcohol on the primary. So one reagent gives us tertiary with this substrate. One reagent gives us secondary. One reagent gives us primary. all from the same starting material. So selectivity is going to be really important. So you want to make sure that somehow your selectivity shows up on your reaction table. Somebody asks you, well, you already know all these. Why don't you just make the reaction table? Well, you actually building the reaction table yourself, going to the back of the book, looking at, oh, this is stereochemistry, this is this is what the general starting thing is. By you going and building this, you've now seen it 2, 3, maybe 4 times. And so it's going to start being easier to remember and easier to get the selectivity. Okay. All right. So that was making alcohols. We added acid across the double bond. We saw that it was Markovnikovs. The alcohols, 2 of the reactions are Markovnikov. One of them's anti-Markovnikov. Okay. So those are important things to write on your list. So now let's shift gears a little bit and do a different mechanism. Let's add a halogen to across our double bond, a bromine-bromine, or diatomic bromine or diatomic chlorine. As it turns out, we're only going to be using bromine and chlorine. Iodine is an endothermic reaction and doesn't work. They just fall off. And fluorine is so reactive it blows up. So you're only going to see me use chlorine and bromine in this class. It's safer. Okay. So the other thing we have to do in this is we have to do room temperature and dark in a non-halogenatable solvent. Okay. So we choose carbon tetrachloride because you can't halogenate. So it's a non-polar. I'm sorry. Yeah, it's a non-polar solvent, and it can't be halogenated. The other polar solvent, if you have to use a polar solvent, you have to use the polar solvent and water. But we actually have a different reaction for that, and I'll tell you that in a minute. And we have to do it dark. Okay. Turns out if you do it heated or in light, it'll actually change the mechanism of the reaction to turn it into a radical. And we'll talk about those in chapter 10, but we're not going to talk about those today. So when you see dark room temperature and carbon tetrachloride, it doesn't participate in the reaction. All it's doing is giving you a solvent that'll work for this reaction. Okay. And so what we're going to do is we're going to add these across the double bond, giving us a vicinal dihalide, adjacent carbons, vicinal dihalide. Don't worry, I'm going to show you how to make a geminal dihalide too. Okay. So when we get this, we don't have any rearrangements. So we're not forming a carbocation. But in this reaction, instead of getting a mixture of syn addition and anti-addition, we only get anti-addition. It's selective. So there must be something about the mechanism that makes it selective in that way. Okay. So how does it work? Well, as it works is the halogen itself is not a very polar bond. And so what it has to do is have it induced polarity by coming close to our double bond here. It induces polarity here, making this partially positive, making this partially negative. So that now that this side's partially negative, it's willing to take these electrons away. And when we look at that, the electrons coming from the double bond make a bond with the bromine here. And 2 of the electrons from here make a bond with the other carbon. When it does that, it creates this halonium ion, bromonium ion cation, or a chloronium cation. And it's a very strange structure, okay? But think about this. You've blocked the top. The top is where already a halogen is. So what you're going to get is the other thing that's now a nucleophile has to come in and attack from the bottom. That's why it gives you anti-addition. It can't go to the top because there's already a halogen there. It has to come to the bottom for an anti-addition. Okay. So in this case here, when we do that, we can see that one of these bonds is going to be a little bit longer than the other. And that's because if you have one side more substituted than the other, it's going to make that bond slightly longer and this carbon slightly more positive. And so what we'll have is that the bromine acts as a leaving group with just the one bond. So it breaks one of the bonds, but it still has the other sigma bond, so it's still attached. And it makes the new sigma bond here. So because of that blocking the top, we get anti-addition from there. Okay. So let's talk about the mechanism a little bit. Okay. So there must be some stereochemical ramifications for this, right? So let's take the same substrate here. We're going to take this cyclopentadiene, and we're going to react it one on the top and see what happens, and one on the bottom and see what happens, okay? So in this case here, both of the carbons are equal. So when we form our initial chlorinium ion, we have it on the top is this one, and on the bottom of this one, okay? And those are actually the same molecule. If you take this and just flip it 180 degrees, it'll look exactly like this. So what's the difference? Well, in this case here, if we have the chloride ion come in and attack in this position, we'll end up with our new bond here, and it'll give us our trans product. Our chlorines are on opposite sides of the ring from each other. So it's our trans product. And we'll get it from this chlorine. This chlorine is going to stay up here, and then this is making our new bond, giving us this isomer. But now, if we have this one and it comes and attacks from the top, we'll end up with the new chloride forming here and the old one being here. And it's also trans, because it has to be, because it's blocking the top, but it's actually the other enantiomer because it attacked the other side. So you actually have chemical ramifications of this. Okay, so how can we use that to our advantage? Well, it turns out if we use different starting materials, different alkenes, we'll get different products. Okay, so let's look at this one right here. So let's start with the cis alkene here. So if we're going to block the top right here, and one of the bromines is going to add there, and the other one's going to add to the bottom here, what we're going to end up with is a mixture of this isomer here. This is the one where the nucleophile attacked on this carbon, gave us 2 stereocenters here. And this is the one where the bromine, let's change colors. When the when the bromine attacked on the other carbon, it gave the other isomer. See the bromines on the bottom here? And again, they're still trans. Turns out, because of this, the cis butene gives us a pair of enantiomers. And it's a 50-50 mixture. There's nothing we can do about controlling it. Okay, so if the cis does that, then the trans is going to give us a pair of enantiomers too, right? Well, actually, it turns out when we make the system here, we have this methyl group and this hydrogen on the same side. Okay, so that when we add our bromine to this side here, it's going to go to one or the other side. So if it goes to this side first, we're going to have this one here. And if it goes to this other side second, it's going to be here. But what's the problem with this? If we rotate this bond 180 degrees so the bromines are next to each other, the methyl group goes to the back and the hydrogen goes out to the front. We have a mirror plane. In fact, both of these will do it. In fact, the trans right here makes a meso compound, non-optically active meso compound. The cis makes a pair of enantiomers in equal portions. Sorry, I'm gonna have to sit down. I thought I could do it. Oh well. There we go. You can still see my hands. There we go. All right. That one. All right. Okay, so let's look at that. So if we can form this reaction and form this intermediate here, and in the previous reaction, we were using bromine as our nucleophile. But what if you want to do something else? What if you wanted to add water or hydroxide or alkoxide or an alcohol? Then you could get alcohol and a halogen. So you'd have a halogen on one carbon and an alcohol on the other. And so we call this the Halohydrin reaction. And it goes by the same mechanism. It gives us anti-addition right here because we form this right here. And then we use something that has a lone pair or a negative charge as our nucleophile, and it'll attack one side, giving us our nucleophile on this side and our bromine on that. So if we attack with water or hydroxide, we'll get an alcohol. If we attack with an alkoxide or an alcohol, we're going to get an ether. So we can get both of those. So this forms an ether. These form an alcohol. But look, we can also put in a large amount of another nucleophile there. And so we can actually get a bromochloro compound. And that's the best way to start getting chiral materials, is to do a separate thing reaction. So The thing is, the first step is the same, and we'll block it from the top or the bottom. And then so when it comes and attacks the other side, we're always going to get trans isomers. And because if they're equal, we don't have control over where regiochemistry. And so we're going to get the pair of enantiomers that are the trans because they're adding trans there. But there is actually a rule here that says if you have a more substituted carbon, when you form your bromonium cation here, this bond is going to be longer. Why? Because this can stabilize a positive charge. And so this bond starts to elongate and gets shorter on this one. So if there's a partially positive charge on that carbon, where's our nucleophile going to selectively attack? It's going to selectively attack at the partially positive. So our water is going to come in and attack here. So notice in this halohydrin reaction, the bromine ends up on the least substituted side. The nucleophile, and in this case water, end up on the more substituted side. So you're going to get a 1-bromo-2-hydroxy compound. Okay. And the other isomer doesn't form because this partially positive charge is driving the selectivity. Okay. And in a more detailed explanation, the regiochemistry of the halohydrin reaction has everything to do with this right here being slightly more positive, allowing us to keep this slightly shorter sigma bond to bromine. And when it attacks as the neutral molecule, you have the protonated alcohol, but then you can use more water as a base and remove it, and you'll end up with hydronium ion as a byproduct. But the first step is the same, which means no rearrangement, no carbocation, and you have selectivity where the OH is going to be if you have a more substituted carbon. Okay. All right, so all of those reactions used the same intermediate, right? They used the 3-membered ring with the halogen in it, giving us anti-addition. So what if you wanted, instead of a halo and an alcohol, what if you wanted a dialcohol? Well, we have 2 different reactions we can do that with. And this makes a 1,2-diol. So the first reaction we have is this osmium tetroxide right here with a little bit of base purity. And we have to have a second step. The second step involves removing the osmate ester formed, okay? So what happens is our osmium tetroxide is this nice square planar material. And so 2 of the oxygens will go and add to the double bond. So these electrons are going to kick out. These electrons are going to go in the osmium. These electrons are going to kick in where that partially positive charge was. And we create this intermediate right here. So notice this is syn addition. Because it's coming in and adding at the same side with both oxygens at the same time, it's always syn addition. Okay. And then we have to reduce off the osmium, and that gives us osmium dioxide. And so that's how the reactions usually run. The only problem is osmium tetroxide is toxic and volatile. It's a toxic volatile liquid. And so what you can do though, is you can trick it. And the way you trick it is you use N-methyl morpholine and oxide, which is this compound over here. Okay. So what this does is we can use catalytic amount of osmium tetroxide. It's going to go through the reaction once and then kick out osmium dioxide. The osmium dioxide is now going to react with this here to take it down to osmium tetroxide again. And then it reacts again to give us our geminal diol. I'm sorry, our vicinal diol. And then it'll keep going back around and around. So you only have to have a little tiny bit about this, but this is the thing that reoxidizes the osmium dioxide to get it to go back into the reaction. Okay. So the other reaction that does this is actually potassium permanganate 4, but it has to be cold. Okay, we're going to see potassium permanganate used in the chapter in the next couple slides where it's used hot. It does a different reaction. And it kind of basically goes through the same mechanism where it has this, it has that same square planar structure. And so it goes through the reaction the same way. But again, it has to be cold. If you don't see cold, it's not going to do this reaction. Okay, so that's how we make a cis diol. Okay, so let's review what we've just learned here. And what we have is that in reactions that make a 1-to-1 mixture, we either form a carbocation or we have something else that gives us, so in both of these right here, we form a carbocation. That's why we get a mixture of syn and anti. In the case of the oxymercurization, demercurization, it also gives a mix of syn and anti. Okay. So when we have a 50-50 mixture, we only have the carbocation and the mercurization. Now, when we get syn-only addition, that's like the catalytic hydrogenation. Catalytic hydrogenation, remember, it sat down on the surface, so it added both hydrogens on the same side. Okay, so that's catalytic hydrogenation. Hydroboration oxidation. In the case of hydroboration oxidation, the boron comes and sits down on top of the double bond, and then the electrons from the double bond reach out and grab the hydrogen, and then the electrons from the boron reach down and grab that carbon. Okay, so it's syn addition as well. And then we have syn addition by hydroxylation. And you think about that osmium tetroxide intermediate, that osmium osmate ester that's formed. And then reactions that only give anti because the double bond had the bromine or chlorine sit on top of it, blocking the top. So you only have anti addition available. And then the halohydrin is where you just come in with an OH instead of a Br. So halogenation or bromination. Okay, so these sets of selectivity, is very important because it really tells you what your products are going to be. Okay, so knowing whether this is syn or anti, that's one of the stereochemical things you want to put in that stereochemical column or regiochemical column in your reaction table. Okay, so now let's do some other reactions. We already took roll, right? So let's do some other reactions right here. And the first one we want to do is we actually want to take that activated bond, right? The sigma bonds are not very activated. Our pi bond is the one that's activated here. And we're just going to cut straight through it, okay? So we're going to cut straight through it and end up making the molecules smaller, okay? So in this case here, we're going to use ozone, and we're going to use either dimethyl sulfide or zinc right here. The reason we use both of those is we call that a reducing workup. We call it a reducing workup. So what's going to happen is our ozone is going to react with our alkene. And again, the ozone has a partially positive charge that's moving around here. And so we have the electrons coming out to the partially positive charge, these electrons kicking in, giving us this ozone ring. But that ozone ring is not very stable. So it immediately rearranges to give you this one right here, the ozonide. In the case of the ozonide, that's pretty stable. You can even isolate that sometimes. But if you add zinc, what it's going to do is it's going to add electrons to the system, and it's going to turn into zinc 2. This is zinc 0. This is going to turn into zinc 2. And when it does that, it's also going to take away one of these oxygens. In the case of the sulfur compound wants to have a bond to oxygen. It's very oxophilic. And so it'll also do the same thing where it comes in and grabs one of those, and then it decomposes to give you one of the oxygen stays on one of the carbons, the other oxygen goes away with the other carbon, and you end up getting ketones or aldehydes. Okay. So this is very specific, ketones, and aldehydes. Okay, and we can make aldehydes because this is a reducing workup. Okay, so questions on that? So what we're doing here is we're just breaking that bond, and so this turns into a carbonyl, and this turns into a carbonyl. So if one of the sides has a hydrogen on it, that will give you the aldehyde. If you have 2 carbons on it, that's going to give you a ketone. So you can look at it specifically that way. Okay. Now you can also do this with permanganate with heat. Notice there's heat and a base here. Okay. In the case of that, what you're going to do is you're going to break the bond to give us a carbonyl compound. Actually, it'll give us the aldehyde first. But because this is so oxidizing, it's an oxidizing type, not the ozone. Remember, we did a reducing workup. Because it's oxidizing, it's going to oxidize any of your aldehydes down to carboxylic acids. So we only get carboxylic acids out on there. But if you have hydrogens on there. No aldehydes, only carboxylic acids. Now, what happens if you have one side that has hydrogens and one side without hydrogens? Well, the side without hydrogen also forms ketones, just like in the ozonolysis reaction. Okay, but if you formed an aldehyde on the other side, it would keep decomposing. So this would decompose down to a carboxylic acid, specifically carbonic acid. Carbonic acid isn't very stable. It decomposes into CO2 and water. So in the case of having a terminal alkyne, an exo double bond here, this side gets chopped off and turned into CO2, and you're left with the ketone all by itself. Now, there's a benefit and a detriment to this. If it's symmetrical, you're going to get 2 equivalents of the same carboxylic acid. If it's not symmetrical, you're going to get 2 different carboxylic acids mixed together. So let's take that and apply it, okay? So what we're going to do is we're going to do this specifically with ozone first, and then we're going to do it permanganate second, okay? So if we do permanganate ozone first, what we're going to see is we're going to break this double bond here, and so we're going to form a carbonyl on this carbon and a carbonyl on that carbon. So that's going to open up to be a ketone, CH3, and this side's going to open up to be an aldehyde with an H on it right here. But what's going to happen over here? If we do the same thing over here, this is going to break to give us a ketone again. We're going to have our carbonyl here. And then this is going to break to give us a formaldehyde, a gaseous aldehyde product, because it's a carbonyl with 2 hydrogens on it. And that's the simplest formaldehyde, the simplest aldehyde we have. Okay, so that means our products are going to be a ketone, an aldehyde, and an aldehyde. All right, now let's do this with permanganate. So if we do this permanganate, what we're going to see is that we're going to break this bond and we're going to form a ketone on this side, but this side is going to turn into a carboxylic acid. Okay, so let's draw that over here, our ketone, CH3, and then our carboxylic acid over here. And then we have our other group coming off here. And if we do it again here, this is going to give us a ketone on this side, and this is going to give us something else. So we're going to get our ketone on this side plus CO2 and water. So see how by choosing the different reagent, we actually get a different product. We had one with 2 ketones and an aldehyde and one with 2 ketones and a carboxylic acid. Just by changing from one reagent to the other. So this is where you want to make sure that you have this kind of selectivity when you're thinking about doing your reaction. Okay, so that was alkenes. Well, what about alkynes? Well, that's just 2 pi bonds, right? Well, it turns out you can do this stepwise. You can take our alkyne and add 1 equivalent of bromine to it to give us our trans dialkene. Why is it trans? Because remember, it's going to form that same intermediate. It's going to block the top so that the other bromine has to come in from the bottom. So it's an anti-addition reaction, which gives us the trans bromoalkane. And then you can add one more equivalent of that, and it'll add across that trans alkene to give us a tetrabromo compound. Okay, so we can do that with chlorine or that. But the cool thing is this is stepwise. If it's a 1-to-1 mixture here, we get the trans alkene, the dihalo trans alkene. Okay, and then if you add another equivalent, you get all the way down to the alkane, the tetrabromo alkane. So do these alkenes also follow Markovnikovs rule? Yes, they do. Okay, you can't really tell on the first one because there might not be any hydrogens here, but when we add our HS, if there is a hydrogen on one side, it will go on that side and we'll end up with a haloalkene. Notice and they're going to add, it doesn't matter where it adds, it's going to give a mixture of it's going to give a mixture of cis addition and trans addition. Okay, and then if you add your second again equivalent, now you get your geminal dihalide because we already had a hydrogen here. The hydrogen is going to add to the side with more hydrogens, and we have our geminal dihalide. So how do we get our vicinal dihalide? We do bromine or chlorine across a double bond. That gives them on the adjacent carbons. How do you get a geminal dihalide? You have to add 2 equivalents of acid to an alkyne. And when you add 2 equivalents of acid to an alkyne, it follows Markovnikovs rule, meaning your hydrogens are going to be on the same carbon and your bromines are going to be on the same carbon. So that's one interesting way to, which reagent would you use to do those 2 different compounds? Okay. So it turns out that cleavage reactions on alkynes only produce carboxylic acids because we don't have 2 carbons available to bond it, to stop it at that site, at the ketone. So we'll end up with just carboxylic acids. And again, if it's a symmetrical one, you'll end up with 2 carboxylic acids that are the same. If it's unsymmetrical, you'll end up with 2 different carboxylic acids. Okay. So for example, and both the hot permanganate and the ozone will do this to them. So this is an example here is if we do it right here, we're going to end up with 1 carboxylic acid with the cyclohexane on it. And then we're going to add with another carboxylic acid with the 1 carbon, carbonic acid, which then decomposes and gives us CO2. So you can get symmetrical or non-symmetrical, and you can get 1 product only if you want. Notice what the other cool thing about this is that in this cleavage reaction, our substrate has gone from 8 carbons down to 7 carbons. We've only lost 1 carbon in turning it into a carboxylic acid by this cleavage method. So that's kind of cool. All right, questions on that? Okay, I told you about the bonus video with all the mechanisms, right? Okay, I'm gonna try to get that done tonight. Okay, so at the end of the book, there's 2 different things that are telling you the reviews. This is the one about the alkenes and alkynes. So we actually did this reaction today. No, we did this reaction, today, right here. So we can say, oh, look, here's how to get geminal dihalides. Here's how to get tetrahalides. We can know how to make our alkenes by doing alkynes. We can make our alkynes by, removing 2 halogens. We can make our alkyne into our cis alkene or our trans alkene. Then we can clip either one of these, giving us probably 2 different products. Don't worry about the carbines. We're not doing carbines right here. So this is a survey. This is a review of all the different reactions that we have from this reaction, going from intermediate to intermediate. So this is kind of where I'm going to ask you, when you're looking at your reaction tables, think, oh, I need to have this. This I can make from here. And then how can I get to these reactions here? So you can say, well, okay, I wanted the tetra, so I had to do 2 additions of bromine. So look at the reactions both in the forward direction and in the reverse direction. That'll really help us when we talk about retrosynthesis. Okay. speaking of retrosynthesis, that's what we're talking about now. So I said before, and the end of last chapter, or the beginning of this chapter, is that we need to start thinking about how to string multiple reactions together, okay? And so you need to have a firm grasp of what kind of reactions you have, hence the reaction table, and be able to look at them forwards and backwards. That's why we want to look at these forwards and backwards, is for this retrosynthetic strategy. So the first thing we want to do is we want to look at the thing and say, did we add any carbons? Okay, if we added carbons, that means we have to have a reaction that makes a carbon-carbon bond, like reaction with a nitrile as a nucleophile, or an acetylide ion as a nucleophile. Or we used something on that reaction and reacted with an alkyl halide. So we need to compare. If you had more carbons, you need to do addition reactions. You need to do some kind of addition reaction or substitution reaction. If you have fewer carbons, you got to look at one of your cleavage reactions. Okay, so that's why you look at that first. Okay, so then you kind of figure out if the functional groups have changed. Okay, so again, we can have a very complex structure, huge hexyl group hanging out over here, but that didn't change. What changed was a functional group here. So what we're looking for is that change, going from this to that, this to that. That's the thing you have to have in your mind when you want to do the chemistry here. Okay, now you then concentrate on the functional groups of the starting materials. And so what you need to ask is, what things would do a reaction that would give me this new carbon-carbon bond, or this new halogen bond, or this new alcohol? What reactions do I have that would do these? And we kind of back up from that. And then what kind of reactions can we do? So what functional groups and what kind of reactions can we do? Then we work backwards. Okay, we start with our product and we say, okay, if I cut one bond off, that's going to give me this next reaction. And then if I do the next thing and I cut one more bond off, that's going to give me a different thing. And if I cut one more bond off, it's going to give me the starting material I'm allowed to work with. Okay, so what we're doing here is we're seeing what bonds we can break, knowing how to make that bond. So we're breaking this bond, knowing what the reagent is to do this. We break this bond, knowing the reagent we need to make that bond. Okay, then we just check the order, reorder it, and do it. So let's do an example of that. Okay, so in this case here, we want to go to this dibromo product from this alcohol. Now we just learned we can make the dibromo product from an alkene. So that's a reaction we can use. And we know what the reagents would be for that. The reagents for that would be bromine and carbon tetrachloride in the dark, room temperature. Okay, so great. But that's not, we're not allowed to use cyclohexene. Okay, but we have a cyclohexanol that we can start with. Can we do something? Do we have a reagent to go from an alcohol to an alkene? I think we learned that last chapter, right? Where we can use concentrated sulfuric acid, would convert this to that. And then this would convert to that. So that is our retrosynthetic attack. We're using reactions we know to make products we do. So what does that do? Now we must work backwards right here. So in working backwards, we have to go to, okay, so that means we need to do sulfuric acid right here is going to give us our cyclohexene. And then our bromine in carbon tet is going to give our system. So we now have our forward reaction set up by looking at what could be a starting material. Questions on that? Okay. It is, so I feel that the reaction table is a very important part of organic chemistry. And not only that, you get to take it on to next semester and remember all the reactions you're going to forget over the summer. So it'll help you. I really strongly believe that. Okay. So, okay, and this is the full stop solve thing. We knew we can make the hexene into the dibromo compound. We knew we can make the hexene from the alcohol. Therefore, our total synthesis is that. Okay. All right, and that is the last of chapter 8. So there's a lot of reactions in this chapter. Okay, so go ahead and review my the slides here, and then the extra video I'm going to put out is going to be chapter 8, all mechanisms. It's not all mechanisms, but it's all the ones that are in the book and a couple other ones. So, and again, they're there for helping you figure out what the intermediate is. Looking at what that intermediate is tells you whether it's going to be syn or anti-addition or a mixture of the two. So you want to kind of have that in your head to help you with that stereochemistry. All right. Questions, comments, concerns? Yes.
So our quiz over chapter 8 is Wednesday.
Yes.
And that's when our homework is.
Yes. Yeah, everything should be back on schedule. We took our exam on time, so everything should be back on schedule. So yay. So and we're even a little early today, so that's kind of weird. But so anyway, I'm going to, on Monday, we're going to do some problems using all of these reactions. And then we're going to start on chapter 9. Horrible chapter 9.
What's in chapter 9?
NMR spectroscopy. So, all right. No, it's fun. I have a really easy way to do it. So, okay. Any questions from home there? Okay, then I'm going to stop sharing. Oh, it's not a touch screen. Right there. Stop sharing and stop recording.